All right, so get this today. We're going to be tackling something that you probably use every single day without even thinking about it.
Okay.
Reinforced concrete staircases.
Oh, wow.
We've got blueprints and calculations and even some excerpts from IS 456.2000, which is the Indian Standard Code for Concrete Design. And we're going to dive deep into all of it.
I'm excited.
Yeah, it's going to be fascinating.
It's so interesting how something so seemingly simple, like, a staircase,
Right.
requires so much engineering and thought and
Yeah.
expertise.
I think stairs are just stairs.
Yeah.
You don't even think about it. But there's so much math and science that goes into making them safe and comfortable.
Right.
So let's start with the basics here.
Okay.
Why is reinforced concrete like the go-to material for staircases?
Well, you can imagine a staircase is almost like a miniature bridge, right? It has to support its own weight and all the people walking on it, and concrete is amazing under compression.
Okay.
You think about all the ancient Roman structures that are still standing today, but it's not so great at handling tension, which are forces that are trying to pull it apart.
Okay, so that's where the reinforcement comes in.
Exactly.
The steel bars that are embedded in the concrete take care of that tension.
Yes, steel is incredibly strong under tension, acts like a skeleton within the concrete, preventing it from, bending and cracking under all that stress.
Okay, so it's like a team effort.
It is.
Concrete for the compression.
Yep.
Steel for the tension.
Exactly.
And that's where this IS 456.2000 comes in.
Right.
Like, it's a rule book to make sure
Yeah.
that these staircases are built to last, covering like material strength and reinforcement requirements, all that stuff.
Yeah, it's not just about throwing concrete and steel together.
Okay.
There are very specific guidelines to follow.
So those guidelines, I mean, they're taking into account a lot of different factors.
Yes.
It's like how many people are going to be on it, what kind of environment it's going to be in, earthquakes potentially.
On all those things.
Okay, so now let's talk about the actual design of the staircase. I've definitely encountered some stairs in my life that are just awkward to climb, like they're too steep or too shallow.
Yeah.
So what makes a staircase comfortable and safe to actually use?
The key is the dimensions of the risers and the treads.
Right.
So the riser is the vertical part of the step, and the tread is the horizontal part where you place your foot.
Right.
And these dimensions need to work in harmony with the natural human stride.
Okay, so too high a riser, and it's like climbing a ladder.
Right.
Too shallow a tread, and you feel like you're taking baby steps.
Yes, exactly.
So how do you figure out the ideal dimensions?
Well, a common rule of thumb is to aim for risers between 150 to 180 millimeters.
Okay.
And the sum of the riser and tread should be between 400 to 450 millimeters.
Okay, so it's all about finding that balance.
It is.
Between the riser height and the tread depth.
Yes.
To get that natural, comfortable stride.
Exactly.
But then how do you calculate the number of risers and treads you need for a specific staircase?
So you start with the overall height between the floors,
Right.
right? Let's say, for example, it's 2.79 meters.
Okay.
You then choose a comfortable riser height within that 150 to 180 millimeter range.
Okay.
Let's say we go with 155 millimeters for this example.
All right, so we divide the total height
Yes.
by the riser height.
Uh-huh.
So 2,790 millimeters divided by 155 millimeters.
Which gives us about 18.
18 risers.
Yeah. So we know our staircase will have 18 steps.
Okay.
Now, to figure out the tread depth, we can use that rule of thumb we discussed.
Right.
The sum of the riser and tread should be between 400 and 450 millimeters.
So if we go with the higher end of that range, 450 millimeters,
Okay.
and we subtract our riser height of 155 millimeters.
You get a tread depth of 295 millimeters.
Okay, so there are basic dimensions.
Exactly.
18 risers at 155 millimeters each.
Yep.
And 17 treads at 295 millimeters each.
Wait a minute. Why only 17 treads if we have 18 risers?
You got me there.
Haha.
Why is that?
Because the top riser leads onto the upper floor level.
Oh,
You'll always have one fewer tread than the number of risers.
that makes sense.
Okay.
Okay, so we know how many steps our staircase will have and how high and deep each step will be. But there's more to it than just the dimensions, right?
Absolutely.
We need to make sure that this staircase can actually handle the weight it's going to carry.
Yes, that's where load calculations come in.
Okay.
We need to consider both the dead load, which is the weight of the staircase itself,
Right.
and the live load, which is the weight of the people and anything they might be carrying on the stairs.
Okay, so how do you calculate those loads?
For the dead load, we consider the volume of the concrete and multiply it by the density of reinforced concrete.
Okay.
And for the live load, building codes provide standard values based on the intended use of the staircase.
So it's not just a guessing game.
No, not at all.
There are formulas and guidelines to make sure these calculations are accurate.
Exactly. And the images that we have here actually provide specific details for the staircase in our example.
Oh, great. So we're not just talking about this abstractly. We're looking at a real-world example.
You are.
Can you walk me through some of the details?
Sure. So the images mention that the width of the staircase is 1 meter, and then they use the riser and tread dimensions to calculate the overall depth of the waist.
The waist?
Yeah.
Like on a person?
It's a term used in structural engineering.
Okay.
It makes sense if you picture it like the side view of a step. It kind of looks like a little waistline.
Okay.
So to calculate the depth of the waist, they use the Pythagorean theorem.
Okay.
Because the riser, the tread, and the waist form a right triangle.
All right. So the square root of 0.155 squared plus 0.295 squared would give us the depth of the waist.
Exactly. And they mention rounding that up to 110 millimeters to make construction easier.
Okay, so they're simplifying things a bit.
For practicality, yes. But even with that, they're still taking into account the key dimensions and applying established formulas to determine the dead load.
Okay, that makes sense. But what are the steel reinforcement? How do they factor that into the dead load calculation?
You're right. We can't forget about the steel we need to calculate the weight of those steel bars, which depends on their size and spacing.
And speaking of spacing, I was just wondering how they determine that.
Yes.
It can't just be random, can it?
Absolutely not. And that's exactly what we'll be diving into next.
Okay.
The fascinating world of reinforcement and how those steel bars are strategically placed to keep our staircase strong and safe. Okay, so let's peek inside that concrete and see how those steel bars, or rebar as they're called, are arranged. It's like having X-ray vision for staircases.
I'm ready. I love it.
Good idea.
I want to see the skeletal structure.
Yeah.
It's amazing to think that there's this whole hidden network of steel working to keep everything from just crumbling, you know?
It really is. And the placement and spacing of these rebars is super important, especially in the waist, that sloping part we talked about.
Right.
Because that's where the staircase experiences the most stress from bending.
Okay, so how do engineers figure out the spacing between those bars? I mean, it can't just be a guess, right?
Yeah. No, definitely not. IS 456.2000 provides guidelines for minimum reinforcement based on the load the staircase needs to carry and the strength of the steel.
Okay.
And our example mentions using HYSD bars,
What is that?
high yield strength deformed bars.
Okay.
And they have a minimum reinforcement of 0.12%.
0.12%. What does that mean?
It's the ratio of the cross-sectional area of the steel to the cross-sectional area of the concrete. So 0.12% means that for every 100 square millimeters of concrete, you need at least 0.12 square millimeters of steel.
Okay, so like with our waist depth of 110 millimeters, we could use that percentage to figure out exactly how much steel is needed in each step.
Yeah.
It's like a recipe for strength, the right proportions of concrete and steel.
I like that. And this example actually takes it a step further with a modification factor of 1.25 for tension reinforcement.
Why do they do that?
It's basically a safety factor.
Yep.
It acknowledges that steel is the key player in resisting tension.
Right, yeah.
And tension is a major force in a staircase. So they're boosting the required steel area by 25% just to be extra safe.
Yeah, it makes sense. It's better to have a little extra strength there than risk a crack.
Exactly.
Okay, so we've got the spacing, but I'm also seeing different types of bars in these diagrams. What's the difference?
You've got your main bars, which run lengthwise along the waist, providing the primary reinforcement.
Okay.
And then you have distribution bars, which are placed perpendicular to the main bars, kind of creating like a grid.
So the main bars are like the heavy lifters.
Yes.
And the distribution bars are there to make sure everything is evenly spread out.
Exactly. Prevent any weak points from forming.
It's a team effort even within the concrete itself.
It is.
But even with all these careful calculations and guidelines, I imagine there are still design challenges that can pop up in the real world.
Oh, absolutely. Real-world projects are rarely as straightforward as textbook examples.
Right. And I'm thinking about those gorgeous spiral staircases you see in some buildings.
Yeah.
Those seem like a nightmare to design.
You're not wrong. Spiral staircases definitely add a whole other layer of complexity.
Okay.
But even with more conventional straight staircases, you can run into challenges, you know?
Yeah.
Limited space and unusual layout. Maybe sometimes you need to add a landing for longer staircases.
A landing, like a little break in the middle of the climb.
Exactly. Landings not only give people a place to pause, but they also act as structural supports, which actually reduce the effective span of the staircase.
Interesting. So it's like breaking up a long bridge into smaller sections with supports in between.
Exactly.
And this example we have actually does have landings, right?
It does. Remember, the total height between floors is 2.79 meters.
Right.
They've split that into 2 flights, each covering 1.395 meters, with 8 treads and 9 risers.
So each flight tackles half the total height.
Yeah.
But how do they figure out where to put the landing?
The landing is usually positioned at a height that's a multiple of the riser height
Okay.
to keep that consistent step pattern comfortable.
Right.
So in this case, the landing height is 1.395 meters, which is exactly 9 times the riser height of 155 millimeters.
Okay, so it all ties back to those initial calculations.
It does.
Wow, it's so fascinating how all these design decisions are interconnected.
It is.
But what about the span of the staircase with that landing in the middle? How do they calculate that?
That's where you have this concept of effective span. It's
Okay.
not just the distance between the floor and the landing. It also accounts for how the staircase connects to those supports.
Okay, I see in the diagrams that they're using X and Y to represent like the portions of the staircase that extend beyond the supports.
Yes, they're basically adding a little extra length on either side to get a more accurate representation of the span that needs to be analyzed, for structural purposes.
Right.
They use a simple formula. The effective span L equals 2 plus X plus Y.
Okay.
And in this case, both X and Y are less than 1 meter. So
Yeah.
the effective span is 2.82 meters.
Okay, so even though like the physical distance between the supports might be shorter, the effective span is taking into account those extra bits
Yes,
that are still carrying a portion of the load.
exactly.
Okay, that makes a lot of sense.
And it highlights how, meticulous engineers have to be to ensure a safe and durable design.
Right.
Speaking of which, we need to circle back to those load calculations.
Okay.
We talked about dead load and live load, but how do they actually put numbers to those concepts?
Yeah, that's a great question because we've been kind of dancing around it, but we haven't actually dug into the numbers.
Right.
And it seems pretty crucial to know exactly how much weight this staircase needs to support.
Yes, you need to make sure it's not going to collapse under the weight of everyday use.
Right.
And luckily, the images do provide specific values for both the live load and the dead load on both the landing and the going, which is that inclined part of the stair.
Okay, so what kind of numbers are we talking about here?
For the landing, they use a live load of 3 kilonewtons per square meter, which is a standard value used in building codes to represent the weight of people and furniture that might be on a landing.
Okay, and what about the dead load on the landing?
They calculate that by adding the weight of the concrete slab itself, which is 25 kilonewtons per cubic meter,
Okay.
multiplied by the thickness of the slab, which is 0.1 meters, plus the weight of any finishes, which they assume to be 1 kilonewtons per square meter.
Okay, so the dead load on the landing would be 3.5 kilonewtons per square meter.
Exactly. And adding that to the live load, you get a total unfactored load of 6.75 kilonewtons per square meter for the landing.
Unfactored, does that mean we're not done with the calculations yet?
Good catch. In structural design, we use load factors
Okay.
to account for any uncertainties, variations in materials or unexpected events.
Right.
But before we jump into those, let's look at the load on the going.
Okay, so is it calculated the same way as the landing?
It's a bit trickier because the going is inclined, so the load isn't distributed as evenly. They use a formula that considers the width of the staircase, the depth of the waist, the riser height, the tread depth, and even the angle of inclination.
Wow, so they're factoring in not just the materials themselves, but how their weight is like acting on that sloping surface.
Exactly.
Okay, that seems like a lot to juggle. So what kind of numbers do they come up with for the going?
Well, after plugging in all the variables, they get a dead load of 5.1715 kilonewtons per square meter for the going.
Okay.
And adding that to the same live load of 3 kilonewtons per square meter used for the landing,
Okay.
you get a total unfactored load of 8.1715 kilonewtons per square meter for the going.
Interesting. So the total load on the going is actually higher than on the landing.
It is.
Why is that?
Well, think about it. The going has to support not only its own weight, but also the dynamic weight of people moving up and down the stairs.
All right, that makes sense.
So we have our unfactored loads for both the landing and the going.
Okay.
Now we need to apply those load factors to get our final factored loads. Which are the numbers we'll actually use for the design calculations?
All right, so that's a perfect spot, I think, to pause and let our listeners digest all this information.
I agree. We've covered a lot of ground here, from basic dimensions to load calculations.
Yeah, we have.
We'll be back soon with the final installment of our staircase deep dive to explain those load factors and wrap everything up.
All right, welcome back. We've been on quite a journey exploring these reinforced concrete staircases, and last time we left off with those unfactored loads for the landing and the going.
Yes, we did.
And I feel like we're about to add a layer of real-world practicality with these load factors.
Exactly. It's time for those.
Because in the real world, things aren't always predictable.
Right.
You might have more people on the stairs than you thought, or maybe the materials aren't quite as strong as you expected.
Exactly.
So these load factors, they're all about adding a margin of safety, right?
They are. It's like adding a buffer to make sure the staircase can handle those just-in-case scenarios.
Okay, so let's crunch the numbers. The images we're looking at say that according to IS 456.2000, the load factor for both the dead load and live load is 1.5.
Okay.
So we multiply the unfactored dead load by 1.5
Yeah.
and the unfactored live load by 1.5 as well.
Exactly. So for the landing, that gives us a factored dead load of 5.25 kilonewtons per square meter and a factored live load of 4.5 kilonewtons per square meter.
So the total factored load for the landing would be 9.75 kilonewtons per square meter.
You got it.
All right. And for the going?
For the going, we end up with a factored dead load of 7.756 kilonewtons per square meter,
Okay.
and the same factored live load of 4.5 kilonewtons per square meter.
So the total for the going is?
That gives us a total factored load of 12.256 kilonewtons per square meter for the going.
Wow. Those factored loads are significantly higher
They are.
than the unfactored ones.
That's the point. They're designed to be more conservative.
Right.
To make sure that staircase can handle, potential variations or uncertainties.
Okay, so now we have these factored loads. What happens next? What role do they play in the actual design?
Well, these factored loads are what help engineers figure out the forces that are acting on the staircase, which then dictates, how much reinforcement you need and the dimensions of the different elements.
Oh, okay, so remember that analogy of the staircase being like a miniature bridge?
Yes.
I'm starting to see it come to life here.
Right. Well, those factor loads are what create the bending moments and the shear forces that the bridge, or in this, the staircase, needs to resist.
So it's like we're figuring out how much weight is pushing down on that bridge and how much force is trying to bend or break it.
Exactly. And the images we have actually show some pretty complex calculations involving equations, diagrams, even calculus to figure all that out.
I think I'll leave the calculus to the experts.
Me too.
But it's fascinating to know how much goes into making sure these things can stand up to, everyday use for years and years.
Yeah. It really is. And the images actually give us a nice visual representation of how those loads are distributed along the staircase.
Okay.
With what's called a loading diagram.
Okay.
So the landing and the going are represented as these horizontal beams.
Okay.
And the factored loads are shown as downward arrows on those beams, indicating the weight that they need to support.
And those arrows are different lengths, right?
They are reflecting the different factored loads that we just calculated.
Okay.
And by analyzing this loading diagram, engineers can figure out the maximum bending moment and shear force at various points along the staircase.
So it's like we're bringing together all these different pieces of the puzzle.
We are.
The loads, the materials, the dimensions, the reinforcement.
It all comes together.
To create this structure that's both functional and safe.
Precisely. And while we've only really scratched the surface here, you now have a much better understanding of how engineers approach the design of these reinforced concrete staircases.
Yeah. I feel like I've gained a whole new appreciation for these everyday structures that we often take for granted.
I agree.
Next time I climb a staircase, I'm going to be picturing all those steel bars working hard inside that concrete.
Right. And you'll know it's not just the concrete and steel holding it all together.
Yeah.
It's also a whole lot of math and science and engineering expertise.
It really is a testament to human ingenuity.
Yeah.
Finding ways to make our lives a little easier and a lot safer one step at a time.
Well said.
Until our next deep dive, keep exploring, keep questioning, and maybe even take a moment to appreciate those remarkable reinforced concrete staircases we encounter every day.